Raptor 3 just broke every record in rocket engine history with 350 bar chamber pressure and a design so advanced it looks unreal. SpaceX engineers are already testing it for the next Starship flights. But here's what nobody expected. Elon Musk just dropped a bombshell about Raptor 4, claiming it will be 10 times cheaper per ton of thrust than Merlin, with even higher performance. How do you top an engine that's already pushing physics to its limits? What engineering breakthrough could possibly make that happen? Let's go back to 2019 when Elon Musk posted something that caught everyone off guard. He admitted SpaceX was worried about Raptor. Not worried it wouldn't work, but worried it might never match Merlin's incredible cost-effectiveness. Musk wrote that Merlin's architecture held world records for thrust-to-weight and thrust-to-cost ratios, while Raptor had better efficiency but might fall short on those two critical metrics. Why would SpaceX's founder publicly doubt his own revolutionary engine? The answer lies in understanding what made Merlin so dominant. Merlin uses a gas generator cycle, a relatively simple design where a small amount of propellant burns in a pre-burner to power the turbopumps. The exhaust just vents away, wasting some energy, but the trade-off is brilliant. Lower pressures, fewer components, easier manufacturing. This simplicity made Merlin lighter, cheaper, and incredibly reliable. Mass production drove costs down so far that Merlin delivered more thrust per dollar than any engine in history. It was the perfect workhorse for SpaceX's reusable rocket revolution. Raptor took the opposite path. It uses full-flow staged combustion, one of the most complex rocket engine designs ever attempted. All propellant runs through two separate pre-burners, one fuel-rich, one oxidizer-rich, before entering the main chamber. This extracts every drop of performance, giving Raptor much higher specific impulse. The engine uses fuel far more efficiently than Merlin ever could. But efficiency came with brutal challenges, chamber pressures exceeding 300 bar, exotic materials to survive the heat, and intricate plumbing that made each engine expensive and heavy. Musk's concern was real. Could this complexity ever become cost-effective? Fast forward to last month. Elon posted an update that changed everything. Raptor 3 will probably be 2 to 4 times better than Merlin in cost per ton of thrust, and will exceed Merlin in thrust-to-weight ratio. Raptor 4 should beat Merlin by 10 times in cost per ton of thrust, with further improvements in TWR and ISP. Read that again. 10 times better, not 10% better, not twice as good, 10 times more cost-effective than the engine that already set the standard. How did SpaceX pull off this transformation in just 6 years? The Raptor 3 numbers tell part of the story. SpaceX achieved a record 350 bar chamber pressure, the highest ever in a production rocket engine. The engine produces 330 tons of thrust while weighing just 1,600 kilograms, giving it a thrust-to-weight ratio around 210. Compare that to Merlin 1D's 180 ratio. Raptor 3 is both more powerful and lighter relative to its output. The specific impulse with the vacuum-optimized nozzle reaches 380 seconds, thanks to an enlarged nozzle designed for maximum efficiency in space. These aren't incremental improvements, they're fundamental leaps in propulsion technology. But Raptor 4 takes the ambition even further. Musk's target is an engine weighing around 1,500 kilograms, producing 330 tons of thrust, pushing the thrust-to-weight ratio above 220. Chamber pressure could exceed 400 bar, entering territory no operational engine has ever sustained. And here's the stunning part. All this performance will cost a fraction of what earlier engines required. SpaceX is targeting under $500,000 per Raptor 4 in the near term, with a long-term goal of $250,000. To put that in perspective, a single RS-25 engine for NASA's SLS costs approximately $100 million. Raptor 4 could deliver similar thrust levels for 400 times less money. How do you engineer something like that? The technical challenges are staggering. Higher chamber pressure means higher temperatures, hot enough to melt conventional engine components. SpaceX developed custom nickel superalloys like SX500, capable of surviving conditions that would destroy standard metals. They're using advanced cooling techniques with integrated channels built directly into the engine body rather than bolted on separately. This reduces mass and eliminates potential failure points. Raptor 3 already introduced a pipeless architecture where plumbing is integrated into the engine structure. Fewer joints mean fewer places for leaks or cracks to develop. Raptor 4 will likely push this design philosophy even further. Engineers are working to eliminate the heavy bolted flange between the thrust chamber and hot gas manifold, replacing it with a welded joint. This single change saves weight and improves reliability. It's pure SpaceX strategy. Find every unnecessary kilogram and cut it. Make every component serve multiple purposes, designed for manufacturing at scale. The Raptor team is competing internally with the Starship structure team, who keep adding mass for payload capacity. Every kilogram the engine team saves, the vehicle team finds a way to use. But the real cost breakthrough comes from mass production, not just clever engineering. Right now, the raw materials for one Raptor engine cost close to $100,000. High-nickel superalloys for the combustion chamber and nozzle are expensive. High-precision components like engine controllers, pressure transducers, and rotation sensors each cost thousands of dollars and require extensive testing to ensure they survive cryogenic temperatures, intense vibrations, and chamber pressures that would crush most sensors. These components must be space-rated, meaning they're tested to failure and validated across thousands of operating cycles. Automation helps, but it's not a magic solution. When you automate manufacturing, you shift human labor from assembly to programming, maintaining, and troubleshooting the machines. The real cost reduction comes from volume. Build 10 engines, and each one costs millions. Build 10,000 engines, and the economics transform completely. Suppliers lower prices for bulk materials. Manufacturing processes get refined through repetition. Workers become more efficient. Quality control improves because you catch problems faster. This is exactly how SpaceX made Falcon 9 affordable. They're now applying that same playbook to Raptor, but at an even larger scale. The cost target of $250,000 per engine might sound impossible, but consider what SpaceX has already achieved. Raptor 1 was a development engine, heavy and expensive. Raptor 2 cut mass by 20% and simplified production. Raptor 3 reduced mass further while increasing thrust by 15%. Each iteration gets simpler to build, more durable, and cheaper to manufacture. Raptor 4's design will have more integrated assemblies, fewer separate components to bolt together, and improved reusability, allowing engines to fly dozens of times with minimal refurbishment. When an engine can fly 50 missions instead of 10, the cost per launch drops dramatically. This brings us to why Raptor 4 actually matters. SpaceX isn't building better engines just to break records. They're building them because the entire Mars colonization plan depends on radically cheap, fully reusable rockets. A Starship carrying 100 tons to Mars needs 33 Raptor engines for the booster and 6 for the ship. That's 39 engines per vehicle. If you want to launch dozens of Starships per year, you need to manufacture hundreds of engines annually. At $100 million per engine, that's economically impossible. At $500,000 per engine, it becomes feasible. At $250,000 per engine, it becomes routine. SpaceX is essentially turning rocket engines into commodities. Raptor uses liquid methane and liquid oxygen, propellants that can be produced on Mars from atmospheric CO2 and subsurface ice. The engine runs cleaner than kerosene-fueled engines, with less soot buildup, making it easier to reuse. The full-flow stage combustion cycle extracts maximum performance from every kilogram of propellant, crucial when you're hauling cargo across 150 million miles of space. And the thrust-to-weight ratio means you can launch heavier payloads or use smaller vehicles for the same mission. The implications extend beyond Mars. NASA plans to use Starship as a lunar lander for Artemis missions. The vehicle's payload capacity could revolutionize robotic exploration, launching probes 10 times heavier than Cassini to destinations like Uranus or Saturn's moon Titan. With Raptor 4's performance, SpaceX could send expeditions to Mercury with heavy radiation shielding or fast missions to the outer planets that cut travel time from years to months. A probe with ample propellant and a robust power source could orbit Neptune for a decade, studying its atmosphere and moons in detail we've never achieved. But all of that depends on one thing: making engines this good, this cheap, and this reliable in massive quantities. That's the bet SpaceX is making with Raptor 4. 6 years ago, Elon Musk worried that Raptor might never match Merlin's economics. Today, Raptor 4 is set to demolish every metric Merlin achieved by a factor of 10. We're watching SpaceX compress decades of rocket engine evolution into just a few years. Chamber pressures that seemed impossible are now routine. Costs that would bankrupt traditional aerospace programs are dropping toward the price of a luxury car. Engines designed for hundreds of flights are being built by the thousands. This isn't just about building a better rocket engine. It's about answering a question humanity has asked for generations. Can we actually afford to become a multiplanetary species? For the first time, the math is starting to work. When a Raptor 4 engine costs $250,000 instead of $100 million, when it can fly 50 times instead of once, when you can manufacture them at automotive production rates, suddenly missions that seemed like science fiction become engineering problems. Mars bases, lunar settlements, deep space probes to the outer planets, all of it depends on engines this capable and this cheap. The race to Raptor 4 isn't finished. SpaceX still has to prove these engines can survive the punishment of rapid reuse, hit those cost targets at scale, and power missions beyond Earth orbit. But if the last 6 years taught us anything, it's that betting against SpaceX's engine team is a losing strategy. What do you think? Can Raptor 4 actually hit that $250,000 price target? Drop your thoughts in the comments. If you want to stay updated on SpaceX's engine development and the future of space exploration, hit that subscribe button and turn on notifications for new space review. Like and share this video if you found it valuable. Thanks for watching, and I'll see you in the next one.